So we have our first exam next week, so I just want to give you an idea of what to expect for that exam. First, about the format of that exam. It's going to be a mixture of multiple choice and short answer. In organic chemistry, right, we need to draw structures a lot of the times for our questions, so you can expect some short answer questions where you will indeed be drawing the structures of those molecules. All right, there will be a mix of both multiple choice and short answer. I just want to note that your multiple choice questions will all be lettered, because numbered, because that has to correspond to your Scantron, right? You got to know what bubble to fill in. Whereas your short answer questions will be lettered, just so that I don't interrupt the numbering scheme of the exam, right? Interrupt the numbering that you're going to need for your multiple choice Scantron, okay? Also, the short answer will very clearly say short answer in the problem, so that you know that you are there to draw something on your exam. All right, so again, a mixture of both. The exam's in the Bulldog Testing Center. As I said at the beginning of the semester, you need your student IDs to make sure that you have that if you do not already, that you get that if you do not already have it. I've sort of written the exam so that I would expect it to take a student about an hour and 15 minutes to an hour and a half, but you have the full 2 hours at the testing center. A lot of students love to ask me how many questions are on the exam. It's my least favorite question because I don't know what you're going to do with that information. But whatever number you need to hear that's going to make you study harder, it's that number. All right? Cool. So today we're going to sort of, what's up?
Are these questions going to be on the test?
Yeah, this is I just pulled this exactly from the exam right here. I really want to see your picture of a house very badly, okay? Okay, so like I said, we're going to focus, I lied. First thing we're going to do is we're going to I just want to be clear about what's on the exam. All right, so exam 1. Okay, the first thing we did were these experimental techniques. And you can expect to see some of these IR and NMR questions on all of your exams this semester, all right? There's gonna be a little bit of IR and NMR sprinkled in throughout the semester. For IR, my expectations are based on our lecture that you can analyze a spectrum. You can cut it up into those relevant regions, the fingerprint region, double bond, triple bond, something with hydrogen region, and that you can identify the peaks in there to tell me the functional group that's present. All right, that was what we learned how to do with IR. In your IR module, there's a practice assignment that has all of those functional groups that I expect you to know, right? Also on your study guide for IR, tells you all those functional groups I expect you to be able to recognize. For NMR, I'm kind of going to pick my battles here. All right, where we're going to start off with what I think are the basics of NMR, which is if I give you a molecule, so given a molecule, can you tell me how many peaks, what the integration of those peaks would be, and for an H1 NMR spectrum, what the multiplicity of those peaks would be. Okay, kind of the hardest thing I could ask you for NMR is to give you an NMR and tell you to draw me the molecule. We're going to start the other way first, which I think is a little easier. Given a molecule, what do you expect to be able to do, or what would you expect to see on its NMR spectrum? All right, so with NMR, we'll kind of ramp it up in difficulty after we have a little bit more practice. This is what I'm going to expect for this particular exam, for our first exam. All right, and then just to kind of complete our list here, our last chapters that we covered were those conjugated dienes. We then went into our chapter on aromaticity, and then we looked at reactions of those benzene derivatives, our electrophilic aromatic substitution, and our nucleophilic aromatic substitution reactions. I guess aromatic substitution would be the blanket term for that chapter. Okay, and like a more detailed study guide, including for IR and NMR, is under our Exam 1 module on Canvas, right? So if you go to Canvas, there's an Exam 1 module. The first page there is a study guide, right? Each chapter broken down by topic. Take a look because it goes through the reactions you're expected to know, as well as details whether or not you're supposed to know the mechanism for those reactions, right? Some reactions we know mechanisms for, not all reactions, and it details which ones you're expected to know on your study guide, all right? Also, under your Exam 1 module are these practice assignments for each chapter. You can actually go back and redo any of your old homework, but it does give you the exact same problems. So that's great if you haven't done it for like a month. But if you just did it yesterday, it's not really the best study guide, all right, or study tool rather. So those practice assignments are just there to be more problems for you to practice on, all right? So again, all that under that Exam 1 module. I'm going to focus on chapter 16, the last chapter here today. If you can make it to next class period, I will focus on our previous chapters in this course. If you need to use that time to take your exam instead, that's fine. There will be no daily quiz. There will be no attendance taken on Monday's class. Cool. All right. So first thing we're going to do before we get started here is we're going to build this tool that's both a study tool that you're going to use, but also something that we're going to be able to use throughout the day today. We're going to build a reagent list for Exam 1. All right, this is kind of the most basic study tool that you should be doing for your exams, is to make yourself a nice little summary of what reactions were covered in that exam. Okay, you'll have something similar to work with on your exam itself, in the sense that I don't expect you to have reagents memorized. There will be a bank of reagents that you're going to be able to pull from, but nonetheless, as a study tool for you, you want to have these reactions kind of summarized. Even better than just having them summarized on a piece of paper would be if you flashcarded them, right? And like had an example on the back of those flashcards. That'd be a great way to study. I'm going to break them down here by category. All right, our electrophilic addition reactions, those that we covered for conjugated dienes. Those were those strong binary acids, hydrochloric, hydrobromic, or hydroiodic reactions. Those will react with those conjugated dienes, those electrophilic aromatic substitution reactions. Those are the ones that have that thermodynamic or kinetic control. In our aromatics chapter, we did learn some benzylic position reactions, but we kind of recovered them in our chapter 16. So I'm going to sort of skip ahead here to our electrophilic aromatic substitution reactions. And we had 6 of those. All right, we had our bromination reaction. We also had our chlorination reaction. We can add a nitro group to the ring, or a sulfonic acid group to the ring. All right, and these last 2 were kind of special in that they were creating new carbon-carbon bonds. They're named after those 2 scientists, Friedel-Crafts. Our Friedel-Crafts alkylation reaction and our Friedel-Crafts acylation reaction. Okay. Also in this chapter, we covered these reactions that convert ortho-para to meta-directors, where we reviewed our benzylic position reactions and then introduced 2 new reduction reactions, where we reduced that benzylic carbon from a carbonyl group to just an alkyl group, or we can reduce our nitro group to an amine group to aniline. All right, so these 4 reactions that convert ortho-para to meta-directors, or vice versa. make this prettier. All right, okay, so our orthopara converting reactions, turning an orthopara into a metadirector, were those oxidation reactions, sodium dichromate under acidic conditions. All right, as well as our allylic bromination or benzylic bromination reaction. Okay, and then we had those two reduction reactions. They're very similar in that they both use the same metal and HCl combination. All right, in one, it's got a follow-up step with sodium hydroxide. The other one just uses heat. You can kind of note, since these are so similar, this is how we reduce our carbonyl group, and this is how we reduce our nitro group. All right, and then lastly, our nucleophilic aromatic substitution reactions. Remember, we have to have that good candidate for a nucleophilic aromatic substitution reaction, but then we're just going to toss in some strong nucleophile. Remember, those strong nucleophiles have those net negative charges, so we're going to have some sodium counter ion in there as well. We made a more exhaustive list of our nucleophiles, which you can look back to in your notes. All right, but any one of these will work for that nucleophilic aromatic substitution reaction. So here's our reagent list for our exam, a good studying guide for your exam, a good summary of the reactions that we should be familiar with. And importantly, we're going to use this tool today here for practice, because what we're going to be doing is not following our electrophilic aromatic substitution reactions. Remember, that's one thing that I could do, is give you benzene and a list of reagents, and you got to tell me what that product is. But what we're going to work on today is you designing your own synthesis pathway, where I tell you we're starting with benzene and creating the following molecules, and you need to figure out what reactions to use and in what order. All right, so that's what we're going to be doing today. You got your little list to pull from. How do we make these two products here? Grab some more water while you work on that. right, so step one, we got to know what reactions to use that will substitute onto that ring a nitro group or a bromo group. All right, I will say we're not going to be using our electrophilic addition of conjugated dienes reactions. We're going to be focusing on this portion here. One thing I would want to do, because I didn't add it up here, but maybe we should just to be clear, in addition to our electrophilic addition reactions for our conjugated dienes, we also had these Diels-Alder reactions. All right, those were between two organic molecules though, so they don't have the same kind of inorganic substrate here, but we can just note that we need our diene and our dienophile in those Diels-Alder. So just to kind of, again, have a summary of the reactions that we covered, we want to note that our Diels-Alder reactions will also be on our exam. They're on our study guide, all that jazz. Okay, again, we're kind of focusing on the bottom half of this chart though. I'm going to go ahead and letter these here. So A, B, C, D, E, F, G, H, I, J, and then K. So if I need to put a bromo group on the ring, which one of these sets of reagents am I going to use here? A, I'm going to need our bromine and aluminum bromide. And what about my nitro group? What reagent am I going to use? C. So let's grab these. Step one, we figure out what reactions to use. Step two, we got to think about the order in which to use those reactions. If we look here, our products, that bromo group and that nitro group are what? Ortho, meta, or para to one another? Meta. They are meta to one another. So then we're going to go in here. That bromine is what? An ortho para or meta director? Ortho. So this one's ortho para. And what about that nitro group? Meta. That one's meta. So which one of these two reactions am I going to do first? Right, so remember, what we put on the ring will direct the incoming substituent to a location. So it's not my second reaction. In this case, it's not my bromine that gets to choose. It's what was already on the ring, that nitro group, that's going to direct that bromine to a specific position. So this is the order in which I would want to use these reactants, these reagents in order to create our product. And if we look down at our next example, these ones are what? Ortho, meta, or para to one another. Ortho. So these are ortho. So again, as we said, that bromo group is an ortho para director. That nitro group is a meta director. So we're going to want to first do our ortho para directing reaction. Oops. And then we can do our nitration reaction. Now, to be clear, I would in this instance get a mixture of both the ortho and para products. So I would have to do some chromatography or something after that if I were in the lab to separate those two out if I wanted a pure sample here. But nonetheless, I would use this pathway if this was my desired product that I was trying to create. All right, cool. So we're just going to kind of sort of ramp it up in difficulty here. Everybody take a second and design a reaction pathway, a synthesis pathway for the following two molecules. All right, so real quick, let's pick out our reactions, that first step. I think that we can hopefully all see that we're going to need that same bromination and nitration reaction, so A and C. Let's grab that. All right, but now I also have this carboxylic acid group on the ring. How am I going to create a carboxylic acid group on the ring? What am I going to need to use? So I'm going to need to use my oxidation reaction, definitely, okay? However, this doesn't add a carboxylic acid group to the ring. This doesn't do a substitution reaction. This was a reaction that occurred at the benzylic position. So in order to oxidize anything, I'm going to need a benzylic position in there as well, right? So what else am I going to have to pair this reaction with? Adding a methyl group. So in this case, our alkylation reaction. All right, so I'm going to want to grab both of these. Okay, so given now that we've picked our reaction, everybody take a second if you have not already, and think about the order in which we're going to perform these reactions in order to get our product. Oops. All right, so looking at our product, these two are sitting meta to one another. My bromo group here we said was ortho-para-directing. And what about a carboxylic acid group with its carbonyl bond directly next to the ring? That would be meta-directing. So I want to put my carboxylic acid group on there first, so I'm going to need to use my alkylation reaction, followed by my oxidation reaction. That puts that carboxylic acid group on the ring, which will then direct that bromine to that meta position. If I look at my next product here, we have that, as we said, meta-directing carbonyl bond. Okay, but my nitro group is also meta-directing. But in my product here, these two are sitting para to one another. So how am I going to do that?
Zinc.
In a different order. I would then have a different product. So regardless of the zinc reaction, I would then have a different product. I wouldn't have a nitro group there anymore, right? So I can't do that, or I wouldn't create my desired product. So I'm instead going to have to be clever about the order in which I do these reactions. If I first do my alkylation reaction, all right, just to kind of follow here, that will put an alkyl group on that ring. And that alkyl group is ortho-para-directing. So I don't want to do my oxidation reaction next, or I'll convert it to a meta-director. So next what I'm going to do is put that nitro group, because my methyl group will direct it to that correct position. right? So again, I'll have a mixture. I'll have to do some chromatography here to separate stuff out. But nonetheless, one of my products that I will get will have that nitro group in that proper position. So that then third, when I follow that up with that oxidation reaction, that'll then oxidize that methyl group to our carboxylic acid group. Okay, so our reactions here, I kind of made a big stink about it, and we put them in a list together, these reactions that convert ortho, para to meta directors. And this past example is a good example about how we have to be clever about when to deploy these in our reaction scheme. We knew we were going to have to use our oxidation reaction in both to create our carboxylic acid product, but when we used it was going to dictate what our product was, right? So again, these reactions here, an important list to kind of keep in mind and to be clever about when you're using in your reaction schemes, in your synthesis pathways. Okay, another one. Butylbenzene. How are we going to make it? Okay, so this is a deceptively difficult one because I have a feeling that everybody's going to say, there's an alkyl group on there. Let's pick our Friedel-Crafts alkylation reaction. All right, so let's look carefully. If we take this benzene and we do that plan, where we take 1-chlorobutane and aluminum chloride. All right, our goal is to add carbon 1 to that benzene ring. But if we did this reaction here, we would not get that product. Instead, what we would get would be sec-butylbenzene, where that alkyl group gets added to that second, or rather added at that second carbon instead of the first carbon. All right, why is that? What happened here that led to this product as opposed to our expected product? Carbocation, right? So, okay, so big thing to emphasize here. One of the things that we learned along with our electrophilic aromatic substitution reactions were these electrophilic species. Remember, these are reactions that we learned the mechanism for, where we have our electrophilic species reacting with benzene. And so for each of these reactions, we detailed what that electrophilic species was, right? In the case of our aluminum bromide and bromine, the bromine attaches to that aluminum bromide, creating a better nucleophile. In the case of our nitration reaction, we have this dehydration to create these nitronium ions. These electrophilic species are something that you should know for each reaction because you should know how to do our reaction mechanism, right? And you need these in order to do your mechanism. For our Friedel-Crafts alkylation reaction, that electrophilic species was a carbocation. And one thing we got to watch out for with carbocations, that is what explains why I got this product over here, is what? What's this keyword I'm looking for? The shifts. Yep, the hydride shift. So in this reaction, we created this primary carbocation. The primary carbocations are not as stable as secondary carbocations. So we had this hydride shift occur, creating our secondary carbocation. All right, so we said we got to watch out for these hydride shift reactions because of that electrophilic species, that carbocation. Okay, so then that begs the question, well then how the heck am I supposed to attach it at that first carbon there? Let's go back to our list of reagents. We're not going to just be able to do a simple alkylation reaction, but what can we do? Does anybody see it? So we can use F. That will stick an acyl group on the ring, and then what are we going to have to do to that acyl group? We're going to have to reduce it using our zinc and HCl. All right, so if we did want to stick that primary carbon onto our ring, we're going to have to do this acylation reaction. 4-carbon acyl halide. And then reduce it using our zinc, HCl, and heat. Cool. All right. So yes, a example to remind us that one, we should know these electrophilic species because we should know our reaction mechanisms and we need them in order to do it. And B, we have these hydride shifts that we have to watch out for specifically with those alkylation reactions. All right, make this one for me. All right, so definitely going to need to use that nitration reaction again. That'll put that nitro group on our ring. How the heck are we going to put a hydroxyl group on our ring? What are we going to have to use?
Zinc and
The nucleophile for sure, right? So that's where I was going with. How do we put a hydroxyl group on the ring? Well, we can note that a hydroxyl group is a good nucleophile, so I can use my sodium hydroxide in order to do it. All right, but then somebody said it, I can't just use these two reactions. What else am I going to need on that ring? A good leaving group. So for the sake of variety, let's pick reaction B, our chlorination reaction. All right, I think it's safe to say that we can use that sodium hydroxide last because I'm going to need these two features on my ring first in order for this reaction to occur. But everybody take a second and think about the order in which we're going to have to perform these two reactions in order to get our product here. right, in order to get a good candidate for nucleophilic aromatic substitution reactions, not only am I going to have that good leaving group on my ring, but it has to be in one of those ortho or para positions. So I'm going to want to stick my ortho para director on there first, right? I'm going to do that halogenation reaction first, then nitrate that ring. I'll get a mixture of products, but again, I can separate those out using some chromatography method, and then I'll add in my sodium hydroxide in order to get my phenol product here, my paranitrophenol. All right, so now we got 3 things on this ring here. How are we going to do it? Alright, so our bromination, we said that we're going to have to use reagent A. What about to stick that methyl group on the ring? E. And what about to stick that sulfonic acid group on the ring? D. So let's grab these. Alright, now let's think about the order in which we're going to have to do them. Alright, well, what should we do first? We're going to want to use our fuming sulfuric acid. That will put a sulfonic acid group on the ring. Alright, and now actually the order of these next 2 reactions don't really matter. And let's think about why that is. So let's just pick one. We're going to do our bromination reaction second. Since that sulfonic acid group is a meta director, it'll direct that bromine to the meta position. All right, but now that I have these 2 groups on the ring, I have to look. My sulfonic acid is a meta director, but my bromine is an ortho para director. All right, so why am I going to get this product if I do my reaction third? Why don't I get my, why does that methyl group get added to a green carbon as opposed to one of the orange carbons? sulfonic acid is stronger, right? Sulfonic acid is a moderate meta-director versus our weak halogen here, which is a weak ortho-para-director. And I will note again, if you switch the order of these two reagents, 2 and 3, you could make that exact same argument. Both of those would be full credit answers on an exam, all right? So in this case, it's sort of arbitrary whether you do the bromination or the alkylation reaction first. Either one would be fine. Cool, so the last thing I want to do for the sake of practice, kind of this same idea here. Let's actually just take the product of our previous reaction. And let's do one more here. Oops, let's brominate this. What would my product be? All right, so similar to before, we now have these two groups on our ring. So we have to consider their directing potential. That hydroxyl group is what? Orthopara or meta-directing? Orthopara. We got that lone pair directly next to the ring here. This is an orthopara director. And what about this nitro group? Well, we already said 100 times. It's a meta-director. And it turns out that my ortho-para positions to my hydroxyl group are the same as the meta positions to my nitro group. So unlike in my previous example where I had this conflict I had to work through, in this case, everybody's in agreement where that incoming group should go. All right? Now, real quick, let me just make a point. Get rid of these color codings here. If I were to draw these two products here, one with my bromine in one position, the other one with my bromine in the other position, I would get marked off on my exam. All right, why would I be marked off in my exam for including both of these products here? Because they're the same thing. Okay, we would have to include multiple products if they are themselves distinct molecules. If we draw the same molecule twice, just in a different perspective, we're going to get marked off. All right, we need to recognize that these two molecules are the same. To be clear, if I picked one of these things up and flipped it over like a pancake, I would have my other structure, right? These are indeed identical molecules. One way that you can convince yourself is to apply your rules of nomenclature. If you went in and named these two molecules, you would get the exact same name, right? Indicating they are indeed the same molecule. So on an exam, I'm just going to want to include one of those because they are not distinct. Cool. We're going to call it there. That's all I got for you. All right. As I said, there are those practice assignments under the Exam 1 module for you to use to study with. And good luck studying.